5, 4, 3, 2, 1. Do we have engine ignition?
Engine start and liftoff. The SS Kalpana takes flight, sights set on the International Space Station. Pitch and roll programmer in.
What if I told you that nature built a rocket engine billions of years before we did? No metal, no fuel tanks, no engineers, just ice dust and the raw power of the sun. And it works perfectly. This is the story of comets, the most elegant machines in the solar system. Most people think of comets as shooting stars, a brief flash across the sky. But that's not what they are. A comet is a frozen world. A dirty snowball, sometimes the size of a city, drifting silently through the outer solar system. It can travel for millions of years without anyone noticing it. Cold, dark, silent. But then, it gets too close to the sun, and everything changes. The sun's heat begins to vaporize the ice on the surface. Not melting, vaporizing, turning directly from solid to gas. This process is called sublimation, and as the gas escapes, it carries dust and particles with it, blasting outward at speeds of up to 1 kilometer per second. This is the tail you see in the night sky. But it's also something else entirely. It's a rocket engine, firing in real time. Here's where it gets extraordinary. Every rocket engine works on the same principle. Newton's third law. For every action, there is an equal and opposite reaction. You push gas out one side, you get pushed the other way. That's exactly what a comet does. As gas jets burst from its surface, the comet gets pushed in the opposite direction. Scientists call this the non-gravitational force. It sounds small, but it isn't. These jets can change a comet's speed by hundreds of meters per second. They can alter its entire orbital path. They make predicting a comet's trajectory one of the hardest problems in astronomy. The famous Comet 67P, studied up close by the Rosetta spacecraft, had jets so powerful they visibly changed its rotation. Rosetta actually had to dodge the jets to stay safe. A spacecraft, dodging the exhaust of a natural rocket engine, 500 million kilometers from Earth. But here's what makes comets even more remarkable. They don't fire uniformly. The jets activate on the sunlit side and shut down in the dark. This means a comet is constantly adjusting its thrust, rotating as it travels, firing different jets at different times, like a spacecraft using attitude control thrusters. Except there's no computer, no guidance system, just physics, operating automatically, perfectly, every single time. Some comets develop multiple jets simultaneously. Comet Hale-Bopp had jets so powerful they were visible to the naked eye from Earth. Millions of tons of material blasted into space every single day, and yet the comet kept going for thousands of years. Comets aren't just beautiful. They may be the reason life exists on Earth. Scientists believe comets delivered water to our planet. Billions of years ago, the same jets that make them natural rockets may have seeded Earth's oceans, and, possibly, the organic molecules that led to life itself. There's also this. Every time a comet passes the sun, it loses material. Slowly, over thousands of years, it shrinks. The engine consumes itself, until one day, the comet breaks apart, or fades into a dark, silent rock. A burned-out engine, drifting forever. But before that happens, it travels billions of kilometers, powered by nothing but sunlight and ice. No fuel, no moving parts, no maintenance. Just the universe, doing what it does best. We spent centuries trying to build rockets. Nature built them before the Earth even existed. The next time you see a comet in the sky, you're not looking at a light show. You're watching an engine fire. If this changed how you see comets, drop a comment below. And subscribe to Galaxy, because we're just getting started.
Comet, it's roughly a 1 in 1,000 model, so the real thing is 1,000 times bigger. The landing site is roughly here, which we're aiming for to deliver the lander. It's the flattest part we could find.
This miniature version of Comet 67P, Churyumov-Gerasimenko, is at ESA's S-Tech facility, where Rosetta was tested before launch.
What we are studying at the Comet with the instruments are basically what are the ingredients, which materials are present, and coming back to one of the objectives of the mission, how complex are the materials present at the Comet.
The chosen landing site is close to areas of activity, so landing will be technically and operationally challenging. It could be a hard or soft landing, as the composition of the surface material is so far unknown. The comet's mass, of around 10 billion tons, and low density suggest it is porous. The lander's instruments will use light, electrical conductivity, magnetism, heat and acoustics to examine the comet's properties on, above and below the surface. Surprisingly, the ALICE, Virtus and Miro instruments have shown that the comet's surface is relatively free from ice, even though it's far away enough from the Sun to remain intact. Instead, it's more of a dark, thermally insulating, dusty crust. But then this mission has been full of surprises, and there will undoubtedly be more to come.